Alright, so today we're going to start complex integration, but not really, because I want to, as I said, ease you into this a little bit. So we're going to review real integration a little bit. Because just as we try to mimic differentiation from real analysis, we want to try to mimic integration from real analysis. So we'll start with integration. We'll do the real version. And then we're going to talk about something which those of you from 265, well, you haven't seen yet in 265, but which are coming eventually, known as line integrals. And actually, well, the next topic in 265 was supposed to be double integrals and triple integrals. But I've been toying with the idea of actually starting with line integrals instead. I haven't decided yet what we'll do. And then I think this will probably be sufficient, but the next thing that we're going to have to talk about before we can actually get into complex integration, things called contours, which is a nice little name, but it's something which is actually really silly, easy. So let's start with integration. So this is going to be nice and basic. You should all know this. Okay, you have a function f, and here we're really sitting in R2. We're not in the complex numbers. This is a real function, f of x. And this function is defined over some interval, A to B. Okay, now the geometric question that you answer in calculus is what?
What's the area?
What's the area under the curve above the x-axis between A and B? Right? Alright. The answer to that question is, of course, what do? You subdivide this and make rectangles. So here's the way we're going to do it. I think probably the way I did it in class at least once is just do this into evenly spaced rectangles. But we're going to be a little less rigid here. So let's see. Well, let's call A x0, and then let's just toss points in the middle: x1, x2, x3, and so forth. And then B will be xn. So these are just n plus 1 points between A and B, including A and B. And I'm going to let P be what we call a partition, and it's just going to be the sequence of points. x0, x1, so forth. Okay, so it's just a sequence of points. And let me call delta xi. That'll be the difference between xi and xi minus 1. Okay. So x1 is just, all right, delta x1 is just x1 minus x0. It's just the length of these things. So they can be different. When we did it in class, maybe we just took delta x and made a fixed one, but that will be more lenient here. And I'm going to use this double absolute value to denote the length of P. Okay? And by length here, I don't really mean like xn minus x naught. What do I actually mean? I actually mean it's going to be the maximum overall I equal 1 to I guess n. The maximum of these delta xi. So it's just the largest interval, right? The largest gap that you put into this line. So when let's say you start with a really big one, the other ones, as long as they're smaller, it doesn't matter what they are. The length is just the size of the biggest one. Okay. So how do we define the integral? Well, the integral, which we write like this, equals, well, what are we supposed to do? Well, first we're missing something. We need space. Okay, what's the space for? It's going to be a limit, right? So when you do the integral, you're supposed to look at the limit as the number of rectangles goes to infinity and the width of each one goes to 0. So the way that we can get the number of rectangles to go to infinity and the width to go to 0, we make the length here, right, go to 0. So we take the limit as the length goes to 0, right? We allow n to do whatever we need it to do so that the length can go to 0. So we sum from I to n, and then what are we supposed to do? We're supposed to look at, well, you need to make a rectangle. So how do you make a rectangle, say, out of this first bit here? Draw a line. Where do I draw the line from? I mean, I have choices, right?
Yeah.
I can do here. That gives me a rectangle. I can do go this way, and that gives me a rectangle. Which one do I choose?
The average.
You do the average. And it turns out it really, in the end, if the limit exists, it's going to exist no matter what you set the rectangles to. So what we're going to do is just choose any point in the middle. I mean, it doesn't have to be the midpoint, just any point in there. And let me call this x1 star. And I'll choose a point there, and that'll be x2 star, that'll be x3 star, and so on. So xi star is going to be when, well, we might as well put it in between the 2 points. So we'll put it in between xi minus 1 and xi. So that gives me a rectangle. So then I can draw that up. It's another rectangle. And that's one we'll. So the area of that rectangle is, well, it's the base, which is delta xi, times the height. And the height is f of x, here it's f of x1 star, and in general f of xi star. It's not like a 5-pointed star, it's just an asterisk. Whatever you like. Right. Now, it turns out that we have this fundamental theorem of calculus, which tells us that we can compute this by finding an antiderivative and evaluating at the endpoints. But that's not the definition, that's just a theorem. Right? The definition is over here on the right. And we're going to try to mimic that definition. That's how we're going to build complex integration. But what's the problem? Why can't I just mimic this immediately for complex numbers? So this is a real function. It eats x's on the real number line. Complex numbers, complex functions eat complex numbers, which do not all live on the real number line. Is that right? So what am I integrating over? On the real numbers, I was integrating from this, it was basically a line from A to B. Right? What do I do for the complex numbers? They're not all lying on one axis anymore. Okay, so before we answer this for the complex numbers, try to answer this for the real numbers. And this is something that we'll also, as I said, see in Math 265. So you'll get to see this again. Let's talk about line integrals. And is it safe to say you guys saw these before in 265 line integrals? Probably. Oh. Bridget?
It was 2 years ago.
2 years ago. Good reason to forget. Okay, so in multivariable calculus, you're dealing with functions with two variables, say. And so their domain is no longer the real line. The domain is now R2. And so you actually have exactly the same problem as we're going to have in the complex situation. Namely, if I want to integrate along some path, the path doesn't have to just live on the real number line anymore. The inputs can be anywhere in the plane. So we're going to want to say, okay, what do you do if you want to integrate over a path like this? So first, what do I mean, integrate over a path? I mean, you want to evaluate the function at the points along this path, just as we did in the real situation. We evaluated the function at every point from A to B, and we saw the value that we had obtained. And then we somehow added up all those values. But in some sort of weird way, because, well, certainly there's an infinite number of values, so they're all very big positive numbers, maybe, so if you add them up, it's just infinity. No, we mean it in a slightly different way, namely this limit here. So what we want to do is imagine that at each point here, because this is a f of x, y, right? Z equals f of x, y. If this is the xy plane, then z maybe comes out this way. At each point, you can say, okay, what's the value of the function? And it pops out to here, right? There's the z value. Okay? And so for each point, you get something. So you get this nice surface that comes out of the board. Okay? And so you might ask, what happens when I add up all those values just the same way that we did over here? So we can write down a comparable definition. So how do we do it? Let's go back over here. The first thing you did, you partition your segment. Okay, well, let's partition this. Okay, so let's break it up. Looks like a little railroad track. Thank you. Okay, so now let's project down each of these points onto the x-axis. So I can again look at these distances on the x-axis. Yep. These can again be my delta xi's. I can again, right, these would be, well, first let me say, there would be my x naught, and there's my x1, and my x2, and my x3, right? And then that would be my delta x1, that would be my delta x2. So this would give me a partition. So this gives me a P. I can again define the length of P in the same way. I can choose points in between. So this point will be x1 star. Right. I can choose another point in here, and that'll be x2 star. Then I can go back up to the function and see what their value is. Just map it right back up, see where it lies. And then I can write down the limit as the length of P goes to 0. The sum I equals 0 to n delta xi. And then, well, now we have a little bit of a problem. I'm not sure what to write. Why am I not sure what to write? I have two variables. I mean, I'd like to start writing and say, the xi star, comma, and now I'm not sure what to write. Okay, so let's go back and see what was happening. Well, this, if I take this x1 star and I map it up, I actually get a point up here. Right? And that's what we maybe should call y1 star. And I take this point up, there's a y coordinate, right? So this y1 star is the y coordinate, y2 star is the y coordinate of that point. Okay, so I know I can write that. I get something, right? It's going to evaluate this function at these points that I choose. It's going to multiply them by the length of this interval. So it'll be this times the value at this point. So you can think it's, you take this point, okay, you take the values out here, and then you just multiply by the width of the interval, right? And that's what it counts out. Okay. Now, I need to, when we wrote down a name for this over here, we said we integrate from A to B. Well, it's not quite as easy anymore, right? We're not just living on the x-axis. Let me just, for now, give a name to this. We call that path, we'll call it C. No? So, this could be, I'd like to say something like, and then again, you can say, what do I put here? And over here I had a dx, because that's where the change was in, right? Dx is coming from the change in x. Where's the change coming from here? Oh, well actually it still is a dx. Something should trouble you. What about y? Why is x preferred here? I mean, isn't that a little bit culturally biased? Yeah. Remember, we always try to avoid cultural bias. What did I just say? We always try to avoid. We always try to avoid cultural bias in math if possible. So what if we did the same thing, but instead of choosing this path along the x-axis that we projected onto, we projected onto the y-axis. Okay, do the same thing. Okay, and this is of course a different choice of, now you're choosing the yi star, and then backtracking to find the xi-star. Okay, so you actually get these two different things. Yeah.
Is f of xy dx dy the same as writing 2?
Good question. You're asking, are these equal? Or no?
I mean, another form of writing is an f of xy and dx dy.
This is with double integration.
Oh, okay.
This is a different topic that we will also get to in multivariable. When you have two integral signs, you have a dx and a dy. But this is different. Okay. Now I should mention there's actually a third line integral that normally gets written down. And it's usually written as ds. And I don't want to say much about it right now, but it's coming from, well, each of these little segments has an arc length. Right? It's just the length of that segment. And that's what this ds is. It's coming from arc length. So, I mean, it's essentially the same sort of situation, only now instead of just having this nice change in y, you're basically writing down the arc length for each one of them. So you can get another one. The only reason I don't want to go into it is it'll be better in 265 to go into it in detail, because I don't want to write down all the arc length formulas and everything until we need them. Okay. So the point is that if we start at least with an appropriately nice path here, and we'll have to make clear what we mean by that, then, well, I mean, you can always write down this limit, and if you're lucky, the function is nice, the path is nice, this limit will exist, and you'll get some number. And in the real world, it actually has a very nice physical significance, which in 265 we'll come into. We will not see as nice a physical significance when we do this for complex integration, but it doesn't change the fact that we can still write it down, and that it's still useful, and that it's still important. It just may not have the same physical interpretation as we had for real.
That's an imaginary interpretation.
It has an imaginary interpretation. That's one way to put it. Okay. Well, actually, it took less time than I thought. Do you have any questions about this? I know you've never seen these things before. Okay. By the way, do you remember when we first did integration last spring? And I wrote down this? Mm-hmm. And then later on, right, we said we'll write it like this. I did this because I wanted you to anticipate this notation. You're integrating over a region. Here we're integrating over a line segment. Here we're integrating over a path. Okay, so I guess we'll sort of start talking about these concepts. So this is just a motivation part of the lecture. That's all this is. Okay, so now the technical sort of hoo-ha. We want to talk about what kind of paths we can integrate over. Right? And we're going to come up with some nice names for different properties. It will seem like we're just little kids playing in the sand for a while, and that's okay. But the homework this week is then quite easy, because it's just here, write down this path, find this path, give a name for this path. So, first, you guys in multivariable, you had to do parametric equations, is that right? Have you seen these?
Again, probably.
Yeah, okay. And have you guys ever seen parametric equations? You have? Oh, that's good.
I think it's one of those things that
So,
That's with T. That's a T and
yeah, that's right, it's with a T.
Yeah, I have.
Okay, good. Ben, have you seen parametric equations with a T?
Probably.
So, for instance, let's say you fire a bullet out of a gun, you know, and you want to know its position, both its x coordinate and its y coordinate. This should sound really familiar to you guys. Does it?
Oh, yeah.
Okay. The horizontal and vertical position are independent of each other. Right? Is that right? But they're both functions of time. Right? So you can write down x of t, maybe that's your the x coordinate, and y. So these are parametric equations is when you give both your x and y in terms of a variable t. And sometimes you can actually eliminate the parameter. The parameter is t. Sometimes you can eliminate it and just write y as a function of x, because there actually is a dependency. And sometimes you can't so easily. So we're gonna be using this language a little bit. We're gonna talk about parameterizing paths and curves. So, well, I think maybe it was on Thursday when we didn't record. We started looking at the following situation. Let's say you have a point, say Z1, and another point Z2. And I connect these with a line segment. Okay, that's roughly a line segment. And I'm going to give what I'm going to call an orientation to the line segment. Okay, an orientation here is going to be a direction. We're going to go from Z1 to Z2. You can imagine somebody having to draw this. And so the question is, how can we write down the equation of this line in terms of, say, the time it takes you to go from Z1 to Z2? And what I told you could do is you say, fine, when time is 1, or when time is 0 rather, you want it to be at Z1. So you might do this, Z1 times 1 minus t. Because now when t is 0, this just becomes Z1 times 1. And when t is 1, you want it to be at Z2. So you might write, is that a telephone? No.
It is.
But not your phone, you were just pretending. Very good. Okay, so Z2, when t is 1, Z2 times t will be at Z2. And what happens at t equals 0? Well, there's no Z2, and t is 1, there's no Z1. And so if you add these together, Z1 times 1 minus t plus Z2 times t, this will give you a line segment that goes from Z1 to Z2. Now, there's another way to write this. Let's see if we expand this out. Let's see, Z1 minus Z1t plus Z2t, which is Z1 plus Z2 minus Z1 times t. Is that right? Z2 times t minus Z1 times t. first, is this really a line segment? I'll give you an incomplete answer. Say, you sure, right? Because this is just a linear function in t, right? It's just in slope-intercept form, right? There's your intercept and there's your slope times t. Of course it's a line. Why is that an unsatisfying answer?
Coordinates, so we don't know which direction.
Well, I mean, z1 and z2, these are complex numbers. They certainly, you can think of them as having a coordinate. Of course, they're complex numbers, which means when I subtract them, I get a complex number. Which means that I have a complex number times t, so I'm saying my slope is some complex number. And that's kind of weird, don't you think? To say, what's your slope? I. It doesn't feel quite right. But nonetheless, nonetheless this works. And why? Well, it's what is z2 minus z1? Well, if you think of the geometric interpretation of vectors, z2 minus z1 is actually this line going from z1 to z2. Remember, if you had two vectors, u and v, starting at the same point, and you wanted to connect them, or you wanted to see what u minus v was, or v minus u. This is v minus u. So actually this z2 minus z1 should just be giving you, as a vector, this is just giving you that line there. So this is not so surprising. And this, what does this z1 do? But that, instead of saying start at the origin and follow that vector, start at z1 and follow that vector. Really go from z1 to z2. Picture. Okay, so it's a line. Okay, so this is nice. We can do this. What if I wanted to make this a little more complicated? Like this. Here's a z3. I'm going to follow the arrow. And then I'm going to go back to z1. Follow the arrow. There are now three components to this. And I can write each one in the same way. Let me use this bottom version. Okay, we're going to use this more often. It's just a tad more useful. So first I go z1 plus z2 minus z1t. So that's the first path. So let me just call it c1. Maybe c1, c2, c3. Okay, and then c2 is z2 plus z3 minus z2t. c2, and then z3 plus z1 minus z3t. Now, notice that each one of these, when time is 0, you start at an endpoint. And when, let's say, we'll call this the initial point. And when time is 1, you end up at the terminal point. Right? So on this one here, this is the initial point, and this is the terminal. This is why, by the way, when mathematicians go to the airport to leave, they don't think they should be in the terminal, they should be in the initial. I personally don't like calling it the terminal because terminal is what happens when you're dead, right? That's it, you die. You know, I don't want to go to the terminal. Whereas George Carlin worried about non-stop flights. He says, "I want my planes to stop." Yeah. You didn't laugh? Okay, so what's my question though? Well, let's say you're trying to give somebody directions, right? On how, not like how to get to Kaiwei's house, right? That's not what I mean. Right? Somebody wants to draw this, okay? And you want them to draw it in 1 second. Okay, maybe that's too fast. How about 1 minute? Okay, we'll give them 1 minute to draw this. Okay, we just want to have it be a 1 though, that's right? Now, for this first one, it's very easy. You could give them this, right? And then they would just follow it, and after 1 second, they'd have drawn it. But now there's a problem. They're supposed to draw the rest of it too. And it's already been a minute. So what do you do? How do you tell them to draw this whole picture in 1 minute?
Say 1/3 of a minute for each segment.
Okay, that's a reasonable idea. Use 1/3 of a minute for each segment.
20 seconds.
20 seconds, all right? So, well, let's keep it with the thirds. Okay, that's fine. That way we don't have to worry about the fact that a minute is 60 seconds. It's one of something, all right? So before each one of these, you let t go from 0 to 1. But Christina's idea is, well, now each one should be only 1/3 of a minute. So should I write 0 less than t less than or equal to 1/3 for each of them?
No.
Why not?
First one stops at 1/3, the second one starts at 1/3.
Right. Once you do the first one, it's been 1/3 of a minute. You don't get to start over at 0 minutes, right? It's got to now. It's still 1/3 of a minute. Now you go to 2
Back
minutes.
to the future.
Okay. But now here's the problem. This equation is supposed to start when t is 0, but now I'm supposed to change this to t equals 1/3. How do I change this equation to factor that in?
Subtract a third.
Subtract 1/3. Is that will that be sufficient? Is that all I have to do?
No.
A third.
What more do I have to
Z
do?
cubed minus this, or z, so 3 minus z2.
So let's see. So in our new one, we can do, well, first, we know in the end it should be this: 0 less than or equal to t less than or equal to 1/3.
Oh, you're starting at the first one. Okay.
Let's start at the first one. Okay. This one was supposed to end when t is 1.
Multiply by 3.
So let's see. If we multiply by, you mean the t by 3?
Yeah.
Okay, so you want to multiply by 3. So you want it to, tell me if I write down anything you don't want.
I don't want that parentheses.
This parentheses.
No, the other one.
You get one, you get both. It's a 2-for-1 deal.
Limited time offer.
Yeah. Well, let's see. Does this work? When t is 0, you're still at z1. When t is 1/3, this becomes a 1. And then you're right back where you start. Okay, good. So it's just going 3 times as fast. Right? It's the same thing. You've just multiplied the slope by 3. Right? So you're just going up the hill 3 times faster. Okay, fine. Now the next one, oops, not 0 anymore. We're going to go from 1/3 to 2/3. So it needs to be the case that when t is 1/3, it's where it was when t was 0 before. right? We should be at z2 when t is 1/3. So somebody suggested that we could subtract 1/3 from t. Now, let's see. When t is 1/3, then this would become a 0. Okay, what's going to happen at 2/3? 2/3, this is going to become a 1/3. Okay, so we multiply by 3. Because now, when t is 1/3, this is 0 times 3 is still 0. When t is 2/3, you get 1/3 times 3, which is again 1. Okay, and then everything else. Okay, let's double check. So t is 1/3, this is 0, that goes away, so you get z2. When t is 2/3, this is 1/3 times 3 is 1, and you're left in z2 plus z3 minus z2, which is z3. Okay, good. Okay, so now it should be pretty clear what to do with the last one. The last one, you go between 2/3 and 1. And what am I going to want to do here? Well, let's see. When t is 2/3, I'm supposed to be at 0. So I just have to subtract 2/3, right? And then, well, when t is 1, I'll get 1/3, but I really want to be at 1, so I better put this 3 back in, and then it should be in the right place. So why are we going through this? Well, we're going to want to integrate over all sorts of paths like this, right? We call them contours. And to actually do that integration, we're going to need to be able to write down an explicit formula for it. Right? So just in the same way that, well, you never really wanted to use this limit definition compute your integrals. You always wanted to be able to use something like the fundamental theorem. So that was very easy. This was baby stuff compared to what we're going to do. Right? You didn't need to know a whole lot there. This was so easy. But with these, you're going to need to be able to write down what your contour is. Right? When you have this C here, you're going to need to be able to write it down. So this whole week is about learning how to do that. Right? Is practicing how to do that. Well, we may get into the contour integration this week, but certainly before we do, we want to know how to do that. Okay, let's see. Okay, we have enough time to do the circle. All right, any questions about the line segment? All right, is this pretty bad, or is this okay? You don't seem very happy. It's okay. You'll do some homework problems and you'll feel better. Ask me a question.
It might be very stupid one though. How did you know Z1 in that line where it's 1 minus t? Or did you just give that?
Oh, I mean, this is sort of from experience. You say, okay, if I'm going from t equals 0 to 1, right? And I know that at t equals 0, I want to start at z1. Then, well, I know that 1 minus t will evaluate to 1 when t is 0. Of course, you might say, well, there's a lot of things that evaluate to 1 when t is 0, right? But I want something which is linear. And frankly, the way I know this is I work backwards from this in my head. I mean, I know this formula, and then in my head, it kind of works backwards.
Okay.
Okay, so let's do another sort of standard path.
favorite over macaroni and cheese now?
If you can come up with well, macaroni and cheese, I mean, is still. I mean, this is more than two-dimensional. But if we just let's say you project macaroni and cheese onto the complex plane, you can work out a formula for it. Sure, you can integrate over it. Absolutely.
Projection.
Wait,
But I don't really like macaroni and cheese.
you don't? What?
Sorry, Kraft.
Over here.
We don't do that.
All right, see.
It's so good, especially if you put like croutons and tomatoes in it, and then like put it in the oven and bake it, and ham. It's delicious. In any case, my question though is that this contour stuff, is that on problem set 5?
Yeah. Should be.
Okay. Because this is problem set
that's
4.
Yeah, you haven't got it.
Okay, I was like,
Yeah. this
No,
is the
problem set 5. I
one.
just put problem set 5 on mine yesterday. Yeah.
Can I see your glasses, please?
Well, no, if I give them to you, I can't see. That's the way they work.
Did
do you wear contacts?
Yeah, I do wear contacts. You guys, the whole time you haven't paid any attention because you've been thinking,
Yeah, you're right, I haven't. I keep on trying to figure out. I'm like, wait, does he always wear glasses?
He looks much more like a professor than a student when he wears glasses.
no, I was up very, very late and I just didn't want to put contacts in when my eyes were already tired.
Kind of figure that out.
What's that?
Kind of figure that out.
I never
That what?
understood. I used to sit here about
The reason why
Oh,
you
that's
wear
really
That I was up late?
like
Yeah.
for weeks on end.
Really?
That's
Okay.
eye drops every once in a while.
Oh my
Oh.
word.
Well, okay.
sometimes.
Let me do another example before I go back and hit this example again. All right.
This seems to be over already.
Is class that bad?
No, it's just a
No
lot.
answer. That's a bad thing. Okay.
No, your class is fine. I swear.
Let's start at the origin and go around the circle of radius 1. Okay. Idea?
What? I'm sorry. What was that?
Okay, this is a circle,
Yes.
radius
that?
1.
Okay.
Oh.
I want to
okay.
start at this point, well, 0
You
radius.
want to go on and go around.
Go around start at the complex number 1 and go around the circle 1 time. And I want to know how do I write that down?
X squared plus y squared.
This is in the complex plane.
So
X squared plus y.
Think we have this nice polar form.
Yeah, e to the theta I from 0 to 2 pi.
The I, so let's use T so we stick with the convention of Remember, theta is always a real number, so T is just as good.
No, it isn't.
Okay, and what is T running from?
e to the it.
I got the E to the it in my classroom with my pips, yeah. I went
I think I need to leave them. I'm gonna like fall out of my chair.
Yeah, mentally.
I think that's a final project.
You could rap.
Actually, no. Can we write a rap and then have you rap it?
Rap it?
That'd
Yeah.
be fun. You guys watch Flight of the Conchords?
Yes.
Oh, I love the hip hoppopotamus.
Oh my.
I'm the hip hoppopotamus, my lyrics are bottomless.
I have a random question actually. Me and Christina were wondering if we could, instead of write one of those essays for cryptography, do like a thing at the sums meeting about like a chapter.
A presentation?
Yeah.
Yeah, I think that'd be a good idea. Yeah.
Yay.
So you're each gonna do one, huh?
Well, we would do it together. It'd just be a really good in-depth.
I see. All right, but before you can do so, you must answer this question. What does T run from?
2 pi.
2 pi, right? I want to go around once. Fine. Okay, what if I wanted to do it in 1 second?
Is 2 pies enough for this class?
I don't know,
Yeah.
Ben, you can eat a pie by yourself, can't you?
No, not that much sugar.
Well, it depends on the size of the pie, I suppose.
Yeah.
You make it small enough, I can eat the whole thing.
If it's just a unit pie,
A unit pie. This is we would need to
But
be.
1 foot, 1 yard.
You don't have to be pi over 8. What if I want to do this between 0 and 1? Then what does my formula need to be?
Over 2 pi.
What's over 2 pi?
It. It's over 2 pi, Adam. It. It's so cool.
Alright, does this work? If t is 0, you get 0, fine. If t is 1, you get 1 over 2 pi. That's not good. That's not right.
I was thinking
You
if
want
you
to
get 2
get
pi,
back to e to the
you're.
t?
It's
Yeah,
like
you- when t is 1, you have to be at 2 pi. So,
multiplied by 2 pi?
how about multiply by 2 pi? Fine, 2 pi t. When t is 0, you get 0. Okay, and when t is 1, you get 2 pi. And did you go around, you gotta make sure you didn't go around too much. For instance, what if I did e to the 4 pi t, pi? E to the in 4 pi. E in 4 pi.
4 pi in?
4 pi mine. Then you would actually go around a second time for sure, assuming that this only took you around once.
Oh, show.
Oh, show. Okay, but of course it can't, this can't take you around more than once. Why not? Well, we know that if you go around once, you're at 2 pi. If t is less than 1, then this is less than 2 pi. So you couldn't have gone past 2 pi, right? Which is what you'd have to do to go around more than once. Okay, so good. So that's how we can go around once in 1 second. And what if we wanted to go around in half a second?
4 pi.
Sure. What if we wanted to go around twice in 1 second? You gotta be careful there. What you're putting in this formula is important, but so is the time interval. It's important too. What if you wanted to go backwards?
Negative.
So if I wanted to, again, go from, say, t equals 0 to 1, but now I want to go around the circle in this direction.
Minus 2 pi.
Sure. If you do a minus, I think, 2 pi it. We'll 2 pi it. Or we'll minus 2 pi it. And sure, as t goes between 0 and 1, you're getting negative angles, so you're going in the opposite direction. But again, when t is 1, this becomes negative 2 pi I, so you're back there, negative 2 pi, which is again back at 1. Cool. What if we went back to our example over here? We had Z1, Z2, Z3. What would I do if I wanted to go backwards along this path? Yeah, right. We just go over here and you could negate all the t's. And I would just reverse it. Right, except, well, let's see. If I made it a minus t, then, well, let's see, what would happen? Would that be okay? Would it still be in the right place? When t was 0, it wouldn't matter that it was a minus t, but when t was 1, it would become minus 1. And all right, it's going to swap these around. You get z1 minus z2, right? Which is how you go the other way. Okay, so it works. So you would, I'll write the first one down. Minus 3t.
Wouldn't you have to make the z1 a negative z1?
Well, let's see, if you made the z1 a negative z1, then when t is 0, you'd be at negative z1. But we want to be at z1. The point itself isn't changing, we're just changing the path, which way we go around. Okay, so here's just a...
Wait, I thought you said you reverse those. No?
What am I reversing?
C2, Z1?
In effect, you are. This minus...
Oh, that minus reverse. Okay.
Yeah, this minus you could put into reverse, right? So this is equivalent to writing...
Oh, so that's the same thing as writing Z1 plus Z1 minus Z2
We'll
times...
see. Actually, you know, this is not quite right. Can you see what's not quite right here? Okay, this reverses. That's fine. But what happens actually? Let's plug this in.
You get
We're
a
too fast.
2z1 minus z2, which is why I was wondering if you should negate before z1.
This isn't the negate. The negation. Okay, let's plug in. T equals 0. T equals 0. You get z1.
Right.
Already, this is actually wrong. We want to get z2, right? This first pass, we want to go this way. Or, it depends, if you want to go this way first or this way first.
Well, you're using the wrong formula to go that way first.
Yeah, let's say, so before we went around the path this way, this time we're going to go around the path this way.
Right.
So you decide where you're actually starting. So if you're starting
No, you're
here,
always starting at Z1.
then we're definitely wrong. Okay, so you want to start at z1. Good. So then we have to go this way, right?
And then
Okay.
you're using the wrong
So where you were using the wrong formula completely, which is the right one. It's actually the one on the bottom, right? We have to run this one first.
Yeah.
We have to do this one backwards. Okay, so let's write it down correctly now. So you have to do z3
I have a sketch.
plus, well, but is z3 right? I'm just copying.
No.
Wow.
What should it be? If we copy this formula, but we do as we had originally intended, which was to just...
But the time is going to change, because that one's going to
Okay.
change to 0 to 1/3.
Sure, right? Originally this was 2/3 to 1, but now we want to go 0 to 1/3. Okay, so let's put that over here. We want 0 to 1/3.
You're
Okay.
just replacing the Z2 from the first equation with Z3.
From the first equation?
You're taking the format of the first equation, but substituting Z2 with Z3, because that's the way you're moving.
So is this
No.
right or wrong? Wrong. Why is it wrong?
Because of what I just said.
Say it again.
That you take the format of the first equation, but substitute it with Z3.
That's right. I mean, this is true, right? We're trying to go Z1 to Z3 instead of Z1 to Z2. So principally, you should just put a Z3 in.
Right.
Okay. My question is, how can we manipulate this equation? The way we took e to the 2it, 2 pi it rather, and just put a minus in front. That was, how do you manipulate it to turn it into the right one? Can you just stick a minus? So the suggestion was you just stick a minus in. And again, of course, this can't work just by sticking a minus in. Because, of course, when you put in a 0 here,
Still get Z3.
you still get a Z3 out. That's the point, is you have to remember what it is you're trying to get. So this one has to start with a Z1 if that's the point you're starting at. And then this one, well, this will be right. Because this minus will flip this around, right? This is the same as Z1 plus Z3 minus Z1 times 3t. And that'll be correct. So you have to fiddle with these things. Okay, well, we're well over time. So tomorrow we'll pick up by looking at things like, oh, we'll draw a little line segment there, and then we'll go around a circle, and then we'll go around half the circle, and then we'll go on the line segment. We'll do paths like that.
Sounds fun. Can we do one like Mickey Mouse?
So what do we need? We need a
It's not very
circle, and then we need another circle up here, and then another circle up here.
Yeah, but it would be one continuous. So you get rid of.
Did you do this?
Get rid of
We
the
can
line.
go there, and then we can go around. Then we can go around.
No.
You don't want to go around something
Yeah,
twice?
I think
Or?
she was more thinking just like from ear to top of the head.
Oh, you mean, okay, so
I know
Like
what
if
you want.
you know how they make the hands as like a headband for kids.
like that?
Yeah.
Or
More,
you can do
but
that.
What are you going with?
Are we still recording?
Who you going with? Oh,
By
yeah.
the way, before you turn it off, so this will be actually an important. I know this is just goofy. Well, no, it's Mickey. This is goofy stuff. But this is going to be important. We're going to talk about what are we going to allow, what rules are we going to allow as far as going over paths more than once and having little points and all sorts of fun stuff. Yeah.
So I wanted to go like.
Ah, I see. This is harder, right? Because this isn't a full circle, so and it's not quite even a circle, so you have to figure out what the angles are, right? Where you're going to start it and stop. It's a little harder to do, but of course you can do it.
Oh yeah.